Right, so here is going to be the worked out explained version of the solution for problem solving session number 4. So that was this particular question. So we're going to start as per usual with drawing our picture. So I'm going to draw it over here, something that looks kind of like this. So I'm going to have a box. It's being compressed onto a spring. It's going to move forward. And then it tells me that some part of this horizontal portion has friction involved. So we're just going to draw some distance of friction. Nothing I draw is ever to scale in these pictures, so that's 1.1 meters. We're then going to go up the incline. Or we're going to, it tells us we go up the incline, so that means that we are going to be going some height up the incline. And then we are going to be coming back down and seeing if we compress the spring. So we have 3 points that we need to concern ourselves with. So 1, 2, and 3, where 3 is we're checking to see if we are compressing that spring again. If we're not, well then we'll talk about how we know that in a little bit. So we have quite a bit of information given. We have our mass, 0.3 kilograms. We can set up our table as well, so points 1, 2, and 3. The X, Y is their thermal energy. So we have all of this. So let's set our Y is equal to 0 to be on the ground. So that's going to mean that for point 1 and point 3, Y is going to be equal to 0 because that incline is frictionless. So the only portion of friction is on this horizontal surface. We're not going to have any thermal energy at point 1, but we will for 2 and 3. We are holding our object in place at 1. At 2, this is our maximum height, so this has to be where we stop. And 3 is we are seeing if we are going to the point where we stop. We've compressed the spring to a maximum value, or we've stopped because of friction. So that means that our kinetic energy is going to be 0 at all points. At point 2, we're not going to be attached to the spring, so that's going to be a 0 there. We are given point 1's value. It's 12 centimeters or 0.12 meters. For 3, we don't know, and that's what we're solving for. And technically, for this question for part A, we are finding the maximum height, so we are going to be looking for Y2. So we do need to find that information. So this is relating to what is given according to the different types of energy. We do have some more information given as well. So because our box is going to be on the horizontal portion of motion when we are traveling through our friction, that means our equation for thermal energy is going to be mu. Normal force is just going to be equal to mg times the distance that we're traveling through our frictional area, which is 1.1 meters. Our mu value is 0.2. So now we would be able to calculate the thermal energy portion as we work through our question. So here we have set up our problem. We have a picture where we've correctly drawn that the friction is only on the horizontal portion, and there's no friction on the incline at all. So we've established where points 1, 2, and 3 are. We don't know if 3 is actually here, but that's going to be our problem for B to look at, so let's ignore it for now. But for 1 and 2, we're just going to go through some distance of friction and see how high up the incline we go. So let's start out by writing out the conservation of energy, and again, we're going to start with kind of that full name version of the conservation of energy. If we go back and look at the table, we have some things that are going to be 0, so we're just going to be able to get rid of those, and we can simplify out our equation as the following. So we have elastic potential energy at point 1, we have gravitational potential energy at point 2, and we have the thermal energy from there should be 2 here, and the thermal energy from point 2 as well. So we can now rearrange this equation, and we're just solving for the height. So it's just the y2 value. So this is what we are going through and solving. So we've, right now, the conservation of energy, we've eliminated everything we have for 0. Now we've rearranged and isolated y2, which we are being asked again to solve for the height the crate goes when it stops. Height being related to y, distance up the incline would be the length of distance along the hypotenuse instead, but here we are explicitly told it is the height we are solving for. So now we can plug in our numbers. Our spring stiffness constant was given as 250 newtons per meter. Again, our distance compressed is 12 centimeters minus 0.2 times the mass of our box, which is 0.3 kilograms, 9.8 meters per second squared, and 1.1 meters for the distance we're traveling through friction. You could have simplified this down a little bit. I personally would rather just divide it by mg once and just have it done with, but you could, if you wanted to, have this term minus mu times the distance. So taking all this and plugging it in, I found that y2 was equal to 0.3922 meters, or if I wanted to round to the correct number of sig figs, which in this case is 2.39 meters. So part A here is very similar to how we've been solving questions in the past. However, we had a very explicit amount of thermal energy that was given, right? We only had a fixed amount of distance our box is going to be traveling through the incline, or sorry, through the friction. So we didn't need to worry about combining anything relating our height and the friction. They were two completely separate calculations when it comes to relating them. Y2 is not related to D in this case. In a lot of the cases we've looked at, we've gone up a friction incline. Those have been related. In this case, the friction is only on a horizontal surface, so it's not at all when we are going up. So B here, so I should probably indicate this is A, is a little more complicated. So for B, what's happening? So if we just kind of draw a quick picture again, we are going from point 2 down the incline. We need to figure out if we are going to make it through the friction and end up at point 3, which is going to be compressing the spring again. So what's going to happen here is we don't want to have to double count for friction. So if we compared point 1 to point 3, we would have to set up this question like this. So we'd have 1/2, oops, that is not capital, v1 squared plus 1/2 kx1 squared plus mgy1. So if we wanted to compare point 1 and point 3, we would do this. So we have, point 1 is exactly the same. Point 3 is going to be a little bit different. So in this case, we would have to see if we have 2 changes in thermal energy. Are we going over this strip of friction twice, or are we only going over it once? Or some fraction of once? So this method would work out, but we need to use the thermal energy both up the incline and down the incline to see if we would compress the spring. So we would need to double check and make sure that we are using 2 times the thermal energy. Now, personally, from what I've seen in general in these types of questions, is a lot of students won't double count for the thermal energy. They'll only treat it as it's there once because that is how the equation is usually written out. So in order to get around that, what we can do is say, well, let's compare 0.2 to 0.3. So when doing that, we're not going to have to include any thermal energy for 0.2. We've already accounted for it by having a Y2 value that is smaller than if there was no friction involved in the system. So we're just going to say, hey, let's pretend we're starting at 0.2 and we want to see if we can slide down the incline and compress the spring. So we're basically chopping the question in half and seeing, well, can this other thing happen, assuming, we've done our calculation correctly. So both of these methods work out. It's just going through and basically saying, if we do part B with this second method, we're pretending that part A didn't happen, other than using the number from part A. If we use this first method, we need to make sure that we're counting for the fact we went up the incline. So we'd have plus change in thermal energy, plus change in thermal energy. So we need to have both directions of going over this friction part if we want to compare 0.1 to 0.3. So I'm going to go ahead and go forward using 0.2 because if I'm being honest, I forget that 2 a lot. So I'm going to get rid of all of the things I know I don't have. Oh, sorry, this is crossed out the wrong thing there. So I have this instead. So I'm going to have mg y2 is equal to 1/2 k x3 squared plus mu mgd. And so what's going to happen here is when I rearrange my equation, I'm going to have a square root. I'm going to have x3 is equal to the square root of 2 mg y2 minus mu d divided by k. So here I've done I've moved everything over and then simplified a little bit, but I have this here. If I'm going through and doing this, and I find out I'm going to be taking the square root of a negative number, that indicates to me that x3 is imaginary, and therefore I'm not compressing the spring. So the second I do my math, and in here I have a negative number, I no longer am compressing the spring. If I get a positive number inside my square root, well then, that value is going to be my x cubed value, but I need to remember I'm taking the, it's the amount I'm compressing the spring. So I would technically want the negative value, which I realized looking at the solution on my other monitor, I didn't put the negative in there. So definitely should have that negative sign because we are again compressing the spring, so we would want the negative value. So let's go ahead and let's do this. So x3 is going to be equal to 2. I'm going to put a big bracket here. So 0.3 kilograms was our mass. 9.8 meters per second squared for gravity. We're going to use the value with extra sig figs for our y2 value. 0.2 is our coefficient of friction, and again, the distance that we are traveling through is going to be 1.1 meters. That's going to be divided by 250 newtons per meter, which again is our spring stiffness constant. And I'm going to need to take the square root of all of that. So when you take the square root, you're going to get plus or minus 0.063641 meters. Again, we're going to want the negative answer for this because we are compressing the spring. So I'll have negative 0.064 meters, or negative 6.4 centimeters, if we wanted to see what that would look like in a slightly nicer looking number. So for part B, we just need to make sure we are setting up this question correctly. Either if we want to compare 0.1 and 0.3, double counting for that friction, and if we're looking at 0.2 to 0.3, not double counting that friction. So we just need to make sure that when we're going through and we're setting up the question, we are being careful with how that's done. Now, if I'm being honest, you will probably not see this question on your exam. Why is that? Because I explicitly took it off of a Physics 130 exam. This is something you are going to be building up into for 130. So you're not going to have something where you're double covering the friction. That is not something I am intending on putting on the exam, especially for problem solving. We haven't done it in class. But this is how you would go through and do that. All right, so that's going to be it for the solution. If you have any questions, feel free to ask.